Hi everyone, I'm Dorsa, and this week I'll be teaching the state-based models, and the plan is for the next couple of weeks for me to teach the state-based models, MDPs, and games, and then after that Percy will come back and talk about some of the later topics. So a few announcements. So homework 3 is out, so just make sure to look at that. And then the grades for homework 1 will be coming out soon. So just, yeah, stuff like that. All right, so let's talk about state-based models. Let's talk about search. So just to start, I was thinking maybe we can start with this question. If you can, let me reset this. So basically, okay, let me tell you what the question is and then think about it. And then after that, I'll get this working. So the question is, you have a farmer, and the farmer has a cabbage, a goat, and a wolf, and it's on one side of the river. Everything is on one side of the river. So you have this river, we have a farmer, we have the farmer with a cabbage, with a goat, and with a wolf. Okay? And the farmer wants to go to the other side of the river and take everything with himself. But the thing is, the farmer has a boat, and in that boat can only fit 2 things. So the farmer can be in it with one of these other things. Okay? So the question is, how many crossings can the farmer do to take everything on the other side of the river? And there are a bunch of constraints. The constraint is if you leave the cabbage and goat together, the goat is going to eat the cabbage, so you can't really do that. If you leave wolf with the wolf is going to eat the goat, you can't really do that. How many crossings should you take to take everything to the other side? Think about it, talk to your neighbors. I'll get this working. Everyone clear on the question? Okay. So the link doesn't work because I can't connect to internet, but all right, so how many people think it is 4? 4 crossings? 5? 5 crossings? 6? 6? Some people think 6. 7? No solution? No solution. Okay, so the point is actually not like what the answer is yet. We'll come back to this question and try to solve it. But I think the important point to think about right now is how you went about solving it. So what were you thinking, and what was the process that you were thinking when you were trying to solve this problem? And then that is kind of the commonality that search problems have, and we want to think about those types of problems where it's more challenging to answer these types of questions than, let's say, reflex-based type of questions. So that's kind of just a motivating example that will come back later. And here's an XKCD on this. So basically, one potential solution is the farmer takes the goat, goes to the other side, comes back, takes the cabbage, goes to the other side, and just leaves the wolf, because why would he need a wolf? Why would a farmer need a wolf? So if you answered 4, you probably were thinking about this. And I guess it has like an interesting point in it, because sometimes maybe you should change the problem. Your model is completely wrong. Maybe sometimes you should rethink and go back to your model and try to fix that. But anyways, so we'll come back to this question. So, all right, so this was our guideline for the class. And we have already talked about reflex-based models. So we have talked about machine learning and how that can get applied. And now we want to start talking about state-based models. This week, we're going to talk about search problems. Next week, MDPs. And then the week after, we're going to talk about games. And if you remember the guideline that we had for the class was, we were thinking about these 3 different paradigms of modeling. Right? We talked about this already. So modeling, inference, and learning. So for reflex-based models, we talked about this already, right? So what would the model be? Well, it can be a linear predictor, or it can be a neural network. So that was the model. And then we talked about inference, but in the case of reflex-based models, it was really simple. It was just function evaluation. You had your neural network, and you would just go about evaluating it, and that was inference. And we also spent some time talking about learning. So how would we use, like, let's say, gradient descent to try to fit the parameters of the model? Okay? So similar thing with search-based models. We want to talk about these 3 different paradigms that we have in the class. And the plan is to talk about models and inference today. And then on Wednesday, we'll talk about learning. And we kind of have the same sort of format next week, too. So we're going to start talking about modeling and inference on Mondays. Wednesdays are going to be about learning. So just to give you an idea of what the plan is. All right, so what are search problems? Let's start with a few motivating examples. So one potential example one can think of is route finding. So you might have a map, and you want to go from point A to point B on the map, and you have an objective. So you want to maybe find the shortest path, or the fastest path, or most scenic path. And that is your objective. And the things you can do is you can take a bunch of actions. So you can do things like go straight, turn left, turn right. And then the answer for the search problem is going to be a sequence of actions. If you want to go from A to B with the shortest path, the answer that one would give is maybe turn right first, and then turn left, and then right again, or any of these sequences. Okay, so this is just a canonical example of what a search problem is. There are a few other examples. So for example, you can think of robot motion planning. So if you have a robot that wants to go from point A to point B, then it might want to have different objectives for doing that. So again, the question might be, what is the fastest way of doing it? Or what is the most energy efficient way of getting the robot to do that? Or what is the safest way of doing it? Like another question that we are interested in is, what is the most expressive or legible way of robot doing it, so people can understand what the robot really wants? So you might have, again, various types of objectives. You can formalize that. And then the actions that you can take in the case of the robot motion planning is the robot is going to have different joints, and each one of the joints can translate and can rotate. So translation and rotation are the type of actions that you can take. So in this case, I have a robot with seven joints, and then I need to tell what each one of those joints should do in terms of translation and rotation. This is my robot, yes. It's a fetch robot. All right, so let's look at another example. So games is a fun example. So you might think about something like Rubik's Cube or this 15 puzzle. And again, what do you want to do as a search problem? Well, you want to end up in a configuration that's desirable, right? So you want to end up in a configuration where you have this type of configuration of the Rubik's Cube or the 15 puzzle. So that is the goal, that's the objective. And then the action is you can move pieces around here. So the sequence of actions might be how you're moving these pieces around to get that particular configuration of the 15 puzzle. Okay? So again, another example of what a search problem is. Machine translation is an interesting one. It's not necessarily the most natural thing you might think about when you think about search problems, but it is actually, you can think about it as a search problem again. So imagine you have a phrase in a different language and you want to translate it to English. So what is the objective here? Well, you can think of the objective as going to fluent English and preserving meaning. So that is the objective that one would have in machine translation. And then the type of actions that you're taking is you're appending words. So you start with the, and then you're appending blue to it, and you're appending house to it. So as you're appending these different words, those are the actions that you're taking. So in some sense, you can have any complex sequential task, and the sequence of actions that you would get to your objective is going to be the answer for your search problem. And you can pose it as a search problem. Okay? All right. So what is different between, let's say, reflex-based models and search problems? So if you remember reflex-based models, the idea was we would have an input, X, and then we wanted to find this F, for example, a classifier, that would output something like this Y, which is a label. It's a +1 or -1. So the common thing in these reflex-based models was we were outputting this one label, this one, in this case, action being -1 or +1. Again, in search problems, the idea is I'm given an input, I'm given a state, and then given that I have that state, what I want to output is a sequence of actions. So I do want to think about what happens if I take this action, like how is that going to affect the future of my actions. Okay, so the key idea in search problems is you need to consider future consequences of the actions you take at the current state.
So like just outputting one thing and then like rewriting the function on like the updated state?
So if you rerun it, so the question is, yeah, is it not the same as like I'm rerunning it? I output a thing and then I rerun it again. And you could do that, but that ends up being a little bit of that would be similar to a greedy algorithm where, like, let's say I want to get to the door and I want to find the fastest way. And right now, if I just look at like my current state, maybe I think the fastest way of getting there is going this way. But if I actually think about a horizon and I think about how this action is going to affect my future, I might come up with a different sequence of actions. Okay? All right. Okay, so, and then we've already seen this paradigm, so let's start talking about modeling and inference during this class. So this is the plan for today. So we're going to talk about 3 different algorithms for doing inference for search problems. So we're going to talk about tree search, which is the most naive thing one could do to solve some of these search problems, but that's the simplest thing we can start with. And then after that, we want to look at improvements of that doing dynamic programming or uniform cost search.
The difference between a search-based problem and a reflex-based problem, the very fact that in a reflex-based problem, the output that you give does not influence the next input, and it does in search.
Yeah, that's true. Yeah, so the output that you get in search problem, it's this action that actually influences your future. Yeah, that's a good way of actually thinking about it. Mm-hmm. All right, so let's talk about tree search. So let's go back to our favorite example. Okay, so we have the farmer, cabbage, goat, and wolf. So let's think about all possible actions that one can take when we have this farmer, cabbage, goat, and wolf. Okay, so a bunch of things we can do is the farmer can go to the other side of the river with the boat alone. So this triangle here just means like going to the other side of the river. The farmer can take the cabbage, so C is for cabbage, G is for goat, W is for wolf. So another possible action is the farmer takes the cabbage, or the farmer takes the goat, or the farmer takes the wolf, and goes to the other side of the river. We also have a bunch of other actions. The farmer can come back. The farmer can come back with the cabbage, come back with the goat, come back with the wolf. So I'm basically enumerating all possible actions that one could ever do. And sure, none of some of these might not be possible in particular states, but I'm just creating this library of actions, things that are possible. Okay? So then when we think about this as a search problem, we could create a search tree, which basically starts from an initial state of where things are, and then we can kind of think about where we could go from that initial state. So the search tree is more of a what if tree, which allows you to think about what are the possible options that you can take. So conceptually, what it looks like is you're starting with your initial state, where everything is on one side of the river. So those 2 lines are the river, the blue lines. And you can take a bunch of actions, right? Like one possible action is you can take the cabbage and go to the other side of the river, and you end up in that state. And that state is not a good state, so I'm making that red. Well, why is that? Because the wolf is going to eat the goat. That's not that great, okay? And every action, every crossing, let's say every crossing takes cost of 1. So that 1 that you see on the edge is the cost of that action, okay? So that didn't really work that well. What else can I do? Well, I can do another action. I can from the initial state, I can take the goat and go to the other side of the river. That ends up in this configuration. From there, the farmer could come back, take the cabbage, go to the other side, end up in this configuration. The farmer can come back. That's, again, not a great state because cabbage and goat are left on the other side of the river. Goat is going to eat the cabbage. That's not great. What else can I do? Well, the farmer can come back with the goat. And then once the farmer comes back with the goat, the farmer leaves the goat, takes the wolf, goes to the other side, comes back, gets the goat again, and then, boom, you're done. So how many steps did this take? Well, 1, 2, 3, 4, 5, 6, and 7. So the ones who answered 7, that was the right answer. And that is kind of the idea of getting to this end state.
The not include the option that would be going back to the previous state, even though that is a valid next step, just because we know that there's...
So you could have this giant tree where you go to different states, but you can actually have like a counter that tells you if I have visited that state, and if you have visited that state, maybe you don't want to go there again because you have already explored all the possible actions from there. We're not done with this tree though, right? Like I've found this good state here, but maybe there's a better way of like getting there. I don't know yet. I haven't explored everything. So what I can do is I can actually explore all these other things that one could do. I'm not going to go over them. But there is another solution, and turns out that other solution also takes 7 steps, so it's not necessarily a better solution, but you got to explore all of that, because there could be another solution later on that is better than the 7 steps. Okay? All right. Yes.
Are these slides up?
They are. They should be. Yeah. Slides are up. Okay. All right. So this is how the search tree looks like. Oh, that's a very good point. Thank you for saying. So for CPD students, I'll try to repeat the questions. I always forget this. I'll try to repeat the questions. The question was the slides up? They are up. They should be up. So, okay. All right. So going back to our search problem. So we can try to formalize this search problem. So let's actually think about it more formally. So what are the things that we need to keep track of? So we have a start state. So let's define S start to be the start state. In addition to that, we can define this function called actions, which returns all possible actions from state. So actions is a function of state. If I'm in a state, it basically tells me what are the actions I can take from there. I can define this cost function. So this cost function takes a state in action and tells me what is the cost of that. In this example, the cost of crossing the river was just 1, but you can imagine having different cost values. We can have a successor function that basically takes a state in action and tells us where we end up at. So if I'm in state S and I take action A, where would I end up at? And that's the successor function. And then we are going to define an isEnd function, which basically checks if you're in an end state where we don't have any other possible actions.
They're basically identical.
You can think of it as a way of like finite state machine type of way of looking at it. Yeah, so like we use a similar type of formalism for MDPs in games too. So it's just a good idea to get like all these formalisms right. But start state, transitions, costs. Okay. Yes.
So success depending on S and A are equal to S.
Say that again. So
cost depends on S, like
cost,
position, and action. And action really depends on the state.
So the action, okay, so action depends on state. So you start from start state where you haven't taken any actions, right? And then from that start state, then you can think about all possible, like right up there. So you're in that start state, and then you can think about all possible actions you can take. And then those actions depend on current state, but they don't depend on the future state, right? So based on my current state, everything is on one side of the river. I can think about all possible actions I can take and where I end up at. And then after that, like the next action depends on that state. So it's a sequential thing. Okay, yes.
You have all the information on the actions and the costs that you could do beforehand. How is this conceptually different than like a min cost flow convex optimization?
You can think of it. Okay, so how is it different from a kind of convex optimization type of problem? So we have an objective here, and you can think of what that objective is, and based on what that objective is, you can have different methods for solving it, right? So you can basically formulate this as an optimization problem, where you look for the solution to the search problem as an optimization problem. That's a perfect way of doing it. And we are going to talk about various types of methods for solving this problem today. All right, so let's look at another example. So this is a transportation problem. I'll just use this. So, okay, so basically what we want to do is we have street blocks from 1 through n. So 1, 2, 3, 4, so on. So these are street blocks, n is here. And what we want to do is we basically want to travel from 1 to some n number. And we have 2 possible actions. So at any state, let's say I'm in state S, at any state, I can either walk, and if I walk, I end up in S plus 1. So if I'm in 3, I'm going to end up in 4. And walking takes 1 minute. Or I can take this magic tram, and this magic tram takes any state S to 2 times S. So if I'm in 3, then I'm going to end up in 6 by taking the magic tram. And the magic tram always takes 2 minutes. It doesn't matter from where to. So if I'm in 2, I'll end up in 4. If I'm in 5, I can end up in 10 by taking the tram. Okay, so I have 2 possible actions in any of these states. And what I want to do is I want to go from 1 to n, and then I want to basically do that in the shortest time possible. Okay? So with the least amount of costs. Does the problem make sense? All right, so this is kind of like what the search problem is. So what we want to do is, first off, we want to just formalize it. And I'm going to do that here. I'm not going to do live solutions because I'm not Percy, and I did that once, and it was a disaster. So we are going to, I've taped these in 2018, but basically we are going to go over it together. So let's just do that. So we're going to define the search problem, this tram problem. So we're going to define a class for transportation problems. So we're going to separate our search problems from our algorithms, because remember, modeling is separate from inference. So let's just have a constructor for this transportation problem. It takes n, because we have n blocks. Okay, so n is the number of blocks. Okay. All right, so then we still have a start state. We are starting from 1, so block 1. And then we need to define is end state. So is end state basically checks if we have reached n or not, because we have to get to the nth block. Okay. All right, so what else do we need? So we have a successor function. We also have a cost function. I'm going to put both of them together because that is just easier. So the successor and cost function, I'm saying let's just give it state s, and then given a state, it's going to return this triple of action, new state, cost. So I give it a state, let's say initial state, and then it just returns all possible actions with the new states I can end up at, and how much does that cost. Okay. So what are my options? Well, if I'm in state s, I can walk to s plus 1, that costs 1. If I'm in state S, I can take the tram, I can end up in 2S, and that costs 2. Okay, so that's how I'm creating my triples. And I need to check if I don't pass the nth block. Remember, like we have n blocks, so we don't want to pass the nth block. Okay, so that's just to make sure that we don't pass it, so we are still below the nth block. And this is what my successor and cost function will return, the triples. Okay, so let's just return that. Okay, so that is my transportation problem. Let's make sure it does the thing the way we want it. So let's say we have 10 blocks, and now I want to print my my successor and cost function. Let's say I'm returning successor and cost for 3. What should I get? So from 3, I can have 2 actions, right? I can either walk or I can take the tram. If I walk, it costs 1. If I take the tram, it costs 2. I'll end up in 4 or 6. Let's just try, I don't know, 9. If I'm in state 9, I can only do one thing. I can walk, right? Because remember, the block is, number of blocks is 10, and I can't go beyond that. So, all right. Okay, so that was, let's go back here. So that was just defining the search problem, okay? And I haven't told you guys like how to solve it. Right? We are just doing the modeling right now. So we just modeled this problem, we just coded it up. Modeling it means what are the actions, what is a successor function, what is the cost function, defining an is-end function, saying what the initial state is. Okay? So now I think we are ready to think about the algorithms in terms of like going and solving these types of search problems. Okay? So the simplest algorithm we want to talk about is backtracking search. So the idea of backtracking search is, maybe I can draw a tree here, is you're starting from an initial state, and then you have a bunch of possible actions, and then you end up in some state, and you have a bunch of other possible actions. Let's say you have 2 actions possible. And this can become, this exponentially blows up, so I'm going to stop soon. All right, so create this tree, and this tree has some branching factor. That's the number of actions you have at every state. And then it also has some depth. So that is how many levels you go down. So let me just define that by D. Okay. And now there are solutions down in these nodes, right? So we want to figure out what those solutions are. And backtracking search just does the simplest thing possible. What it does is it starts from this initial state, and it's going to go all the way down here. And if it doesn't find a solution, it's going to go back here and then try again and try again. And it's going to go over all of the tree because there might be a better solution down here too. So it needs to actually go over all of the tree. Okay? So I'm going to have a table of algorithms, because we're going to talk about a few of them here. Algorithms. What sort of costs they allow in terms of time, how bad they are, in terms of space, how bad they are. So if you've taken an algorithms course, like some of these are probably familiar. So, all right, so we talked about backtracking search. Backtracking search. That is basically this algorithm that goes through pretty much everything. And it allows any type of costs. So I can have any costs, right? I can have pretty much any costs I want on these edges, because I'm going over all of the tree. It doesn't matter what these costs are. Okay? So how bad is this in terms of time? So in terms of time, I'm going over the full tree. By going over the full tree, then this is going to have this exponential blow up where I'm looking at order of b to the d, where b is again my branching factor, and d is the depth of the tree. Yeah. Because in terms of time, this is not a good algorithm. Right? In terms of time, I have to go over everything in the tree, and that's the size of my tree. Yeah. And in terms of space, what I mean is I need to figure out what was the sequence of actions I needed to take to get to some solution. So let's say that my solution is down here. If my solution is down here, then for me, I need to store a bunch of things to know how I got here. And the things I need to store are the parents of this node, and that is depth of d. So in terms of space, this algorithm takes order of d. Because that is like the things that I need to store in my memory to be able to recover like the solution when I get there. This question.
Everything, shouldn't the space be big or be a b to the d as well? Because until you get to that, you need to have the space to have everything, right?
You can forget them, no. So actually, we'll talk about BroaderFirst Search later, which does require have a larger space. So the reason you can forget it is the only history that I need to keep track of is this particular branch, right? I don't need to figure out, I don't need to keep track of, actually the history of all these other nodes. I can throw those out. But for something else like BroaderFirst Search, where we'll talk about in a few slides, you actually need to keep track of, the history of everything else. So let me get back to that in a few slides. But for this one, basically, the idea is, I want to know how I got there. To know how I got there, I just need to know the parents.
And the minimum cost to reach a point, or is it to find whether you can or cannot reach a certain point?
So it depends on what your objective is. It really depends on what the search problem is asking. So in the case of that farmer goat example, the search problem is asking you want to move everything to the other side of the river, so you have that criteria, and you want to find the minimum cost one, so you also have that other criteria. So it really depends on what the search problem is asking, and some of these nodes might be solutions, some of them might not be solutions. So it really depends. All right, so let's just look at these on the slide. So the memory is order of d. It's actually small. It's nice. In terms of time, this is not a great algorithm, right? Because even if your branching factor is 2, if the depth of the tree is 50, then this is going to blow up immediately. So a lot of these tree search algorithms that we're going to talk about, they have the same problem. So they pretty much have the same time complexity. We are going to just look at very minimal improvements of them. And then after that, we'll talk about dynamic programming and uniform cost search, which are polynomial algorithms that are much better than these. Okay. All right. So let's go back to the tram example, and let's try to write up what backtracking search does. So, all right. So we defined our model. Our model is the search problem, this particular transportation search problem. It could be anything else. And now we are going to kind of have this main section where we are going to put in our algorithms in it, and we're going to write them as general as possible so we can apply them to other types of search problems. Okay? So let's define backtracking search. It takes a search problem. It can take the transportation problem. Okay? All right. So, and then we're going to basically, in backtracking search, what we are doing is we are recursing on every state, given that we have a history of getting there and the total cost that it took us to get there. Okay? So at the state, having gone some history and some accumulated costs so far, we are going to basically recurse on that state and look at the children of that state. Okay? So we're going to explore the rest of the subtree from that particular state. Okay? All right, so how do we do that? Well, we got to make sure that we're not in an end state, or if we are in an end state, Like we can actually update the best solution so far. Okay. So let's put that for to do. So the bunch of things we need to do. We need to figure out if we are in an end state. If we are, well, we got to update our best solution. If we are not in an end state, then we are going to recurse on children. Okay. All right. So we can do that later. And then in general, this recurse function is going to, we're going to call it on the start state. So let's actually do that too. So what backtracking search does is it calls this recurse function on the initial state that we have with history of none, right? Like if we don't have any history yet, and cost is 0 so far because we haven't really gone anywhere. So we start with the start state, we call recurse on it, okay? And how do we recurse on children? Well, we have defined this successor and cost function. So by calling that successor and cost function on state, then we can get action, new state, and cost. So we get this triple of action, new state, and cost. Okay? And then we can basically recurse on the new state. I'm not putting the histories right now in this code, so you need to keep track of the history too, but let's just not worry about the history. Oh, I guess I'm putting it in this one. In the later ones, I will not put them. But basically, the history is keeping track of like how you got there, and total cost is going to be what you've got so far plus the cost of this new state action. Okay, so we need to keep track of the best solution so far. So I'm just going to define a dictionary here just to make sure that we keep track of it and for Python scoping reasons. Okay. And then the place we are going to update our best solution so far is that to-do that is left, right? So if we are in an end state, then we can actually update the best solution so far. Okay. And what do we want in our best solution? Well, we want to know what the cost is. So we can start with cost of infinity, and anything below infinity is better. And then we are going to start with a history of empty, but we are going to fill up that history too. Okay. So that's the initialization of best solution so far. Then we are going to update that, right? If we are in an end state, if the total cost that we have right now is smaller than the best solution so far, then we are going to update that best solution. And we are going to update its history with whatever its history is. All right, and that's it. That's backtracking search. Okay. So let's just make sure it does the thing. So to do that, we are going to, actually no, we got to return the best solution so far. All right. So now we have defined this transportation problem. Now what I want to do is I want to call backtracking search on the transportation problem. Okay. So that all sounds good. I need to write a print function also to be able to print things. So I'm going to just write a generic print function that we can call on any of these types of problems. So let's define a print solution function that just like prints things the way we want them. So we get the solution. We're going to just unpack the cost and history and just print the cost and history nicely. Okay. All right, so I can use this print solution for pretty much all the other algorithms we'll talk about today too. And we're going to talk about how we get there with the history. So now I have my print function, I have my backtracking search algorithm, I've defined my transportation problem. I can just call it on this transportation problem with 10 blocks. So as you guys can see here, so the total cost is 6. So what this means is for going from city 1 to city 10, then this is the best solution. I got to walk, and then after that take the tram. Because like I end up in 5, and then after that it's actually worth taking the tram and paying cost of 2. Let's try it out for 20. What do you think is the answer for 20? So similar to before, walk, until we get to 5, then we take the tram, then we take the tram again. Cost is 8. And then if it is 100, it's a little bit more interesting if you have 100. So you're walking, and then you're taking the tram, and you get to 24, and you have that one step to get to 25. which is a good state because then you can just multiply that by 2. So you walk for that one step and take the tram again. Okay? So what if I want to try out a much larger number of blocks? So is this going to work? No, because remember that time was order of b to the d. That wasn't that great. So let's try that. Well, we got maximum recursion depth. You can fix that. So let's try fixing that. So you can set your recursion limit to be whatever. So you could try that. Is this going to work? Well, now it's just going to take a long time, right? So it's not going to give you an answer because it's going to just take a long time. So, all right. Okay, let's go back here. All right, so that was backtracking search, right? So all it was doing was just going over all of this tree. And it was taking exponential time, as you saw, and we just tried it out on that transportation problem that we defined. So we just defined a search problem. We use this really simple search algorithm to find solutions for that. And then that's what we have so far. So now what we want to do is we want to come up with a few better improvements of this backtracking search. Again, don't get your hopes up. It's not that big of an improvement, but we can do something better. So the first improvement we want to make is by using this algorithm called depth-first search. Some of you might have heard of it. DFS, or depth-first search, okay? So the restriction that DFS puts in is that your cost has to be 0. So your cost has to be that. Let me actually draw a line between them. So, okay, so we're talking about DFS now, and the restriction is the cost has to be 0. So what DFS does is it basically does exactly the same thing as backtracking search, but once it finds a solution down here, then it is done. It basically doesn't like explore the rest of the tree. And the reason it can do that is the cost of all these edges is 0. So if the cost of all these edges are 0, then if I find a solution, I found a solution. I don't need to like find this better solution because that is good enough. Like anything I find also has a cost of 0. So might as well just return the solution. Like an example of that is if you have Rubik's Cube, like if you find a solution, then you found a solution, right? There are a million different ways of like getting to a solution, but like you just want one. And then if you find one, then you're happy, you're done, okay? So as you can see, this is a very, very slight improvement to backtracking search. What happens is in terms of space, it's still the same thing. So it's order of D. So in terms of space, nothing has changed. It's pretty good. It's order of D. In terms of time, in practice, it is better, right? Because in practice, if I find a solution, I can just be done. Don't worry about the rest of the tree. But in general, if you want to talk about it in theory, then the worst case scenario is just trying out all of the trees. So you write it as worst case scenario, it's order of B to the D. So nothing has really changed in terms of exponential blow up. Yes.
How you draw that tree, it seems to imply that the subproblems do not overlap, right? Because you're kind of branching out in kind of different states, but in fact, the subproblem could overlap. So similarly in the trend problem, you can get to the same place through different history, but the rest is the same.
Yeah, so you can, so the question is, yeah, do subproblems overlap here or they don't? So you could actually have it in a setting where subproblems do overlap, but you could actually add this extra like constraint that says if I visited the state, then don't add it to the tree. So you have that option, or you have the option of like going down the tree with some like particular depths and not trying out everything. In the setting that we have here, yeah, like we are basically trying out all possible. Like I'm talking about the most like general form where you're going over all the states and all possible actions that could come out of it. All right, so that was DFS. Okay. So the idea of DFS, again, is you're doing backtracking search, and then you're just stopping when you find a solution because cost is 0. Okay, so in terms of space, order of D. In terms of time, it's still order of B to the D. Okay? All right. So that was DFS. We have another algorithm called breadth-first search, BFS. And this is useful when cost is some constant, but it doesn't need to be 0. It's just some positive constant. So what that means is all these edges have the same cost, and that cost is just C. So I have the same cost pretty much everywhere. Okay? So the idea of breadth-first search is we can go layer by layer. Like we're not going to try out the depth. Instead, what we can do is we can go layer by layer, try out this layer and see if we find a solution here. Remember, the tree doesn't need to go all the way down here. The tree could end here, or like at any of these nodes, right? Like I can have like a tree that looks maybe like this. I have a solution here. This tree doesn't need to be like this nicely formed. Like I can have a tree that looks like this. Okay? So if I have a tree that looks like this, with breadth-first search, I'm going to try out this layer, see if this guy is a solution. If it's not, I'm going to try this guy, if this is the solution. If not, I'm going to try here, here, and then when I find a solution, when I get here, I'm done, right? Because like, if I find a solution here, I know it took 2C to get here, like 2 of these C values. And if there is any other solution anywhere else in this subtree or in this subtree, those solutions are going to be worse than this, because they're going to just like take like, they're going to have a higher cost. Okay? So because the cost is constant throughout. Okay? So then it's useful if your solutions are somewhere like high up in this tree, and then you can find it. So in terms of time, I get some improvements here, because I can call this depth, this shorter depth, d, small d. I'm going to call this shorter depth, small d. And in terms of time, it's still exponential, but it's order of b to the small d. And this is actually a huge improvement, because if you think about it, the trees exponentially become larger. So these like lower levels are a lot of things that you need to explore. If you have like branching factor of 10, the next layer has 100 things in it, right? So going down these layers is actually pretty bad. So the fact that with breadth-first search, I can improve the timing and limit it to a particular depth, that's pretty good. Still exponential, but pretty good.
That you have no negative costs at that point, you can also assume this is the best solution.
Yeah, you can assume that this is the best solution. Yeah, exactly. So you're assuming that there are no negative costs. So at this point, I know this is the best solution. I'm done. Like I call it, and then I don't like explore anything else. The problem with breadth-first search is there's a question there. Sorry.
So the same?
Yeah, we're assuming all the costs are the same, because maybe like all the costs are one. If I don't assume that, if all these costs are 100, and then like there might be like some other. Like, yeah, you need to explore the rest if they're not the same, basically. All right. So the problem with BFS is, in terms of memory, we are losing. In terms of memory, you need to actually keep track of the history of all these other, like all the nodes that you have explored so far. So in terms of memory, this is going to be order of B to the D, kind of similar to the time. And the reason is, I have explored this guy. And then after exploring this guy, I need to still have like a history of where it's going to go, because next time around when I try out this layer, I need to know everything about its parent. And when I explore here and this is not a solution, I need to store everything about this, because maybe I don't find a solution in this level and I need to come down. And when I come down, I need to know everything about these nodes. So I need to actually store pretty much like everything about the tree until I find my solution. And then that's where you'd lose like in breadth-first search. In terms of space, it's not going to be that great. So in terms of space, it's now order of B to the D. It's a lot worse than what we have had. In terms of time, it is better. It's still exponential. It is better. Okay? All right. Okay. So now let's talk about one more algorithm. And then after that, we jump to dynamic programming. There is a question back there.
One thing though, the small d can be the same as the big D, right? So
it can, yeah. So it is exponential. I agree. Small d can be the same as big D, but in practice, if small d is not the same as big D, we're winning a lot, because yeah, these lower layers are so bad that people actually like to call the fact that we are order of b to the small d rather than big D. Yes.
DFS, you did worst case scenario for the time, but not for EFS.
So DFS needs to go all the way down to these lower levels. But BFS can stop at every level because it's doing level by level.
Well, now for breadth.
Yeah, so the reason is, yeah, so like you were saying, okay, so in DFS, we were also saving some time, right? Like, why aren't we like calling that out? And then the reason is with DFS, you still need to get to these like lower layers. And that is the place that you're losing on time. So the fact that you're still like losing on time, and sure, like you haven't explored these other ones, but you have already got to these lower trees, like so far, that's pretty bad. So that is why we're calling it order of b to the d in a worst case. Okay. All right, so this last algorithm I want to talk about is an idea that tries, it's a cool idea. It actually tries to combine the benefits of BFS and DFS. And this is called DFS iterative deepening. So what this algorithm does is it basically goes level by level, same as BFS, because then that way, if you find a solution, you're done, everything is great, right? But what it does is for every level, it runs a full DFS. And it feels it's going to take a long time, but it's actually good because again, if you find your solution like early on, it doesn't matter that you have ran like 1 million DFSs so far. So it's kind of like an analogy of it is imagine that you have a dog and that dog is DFS and it's on a leash and you have like a short leash. And when it is on that leash, it's going to do a DFS and try out and search all the space. And it doesn't find anything. So it comes back and then you're going to extend the leash a little bit and then it's going to do everything and like search everything and do a DFS. Comes back, doesn't find anything, you extend the leash again. So that's the idea. Like extending the leash is this idea of extending your levels. Okay? So how does DFS iterative deepening do? Yes?
If what we're looking for is at the very bottom of the tree, it's even worse than both of them combined.
Say that again, sir.
Sorry, if what we're looking for is at the very bottom of the tree, it's not going to be even worse than.
Yes, exactly. Yes, that's okay. That's a good point. So the point is, the point that I mentioned is, if your solution is like here, you're screwed. It's worse than DFS or BFS, right? You're doing all these DFSs through like a bigger, like higher level BFS, and it's a terrible situation. But again, in practice, like we are hoping the solutions are not going to end up like down this tree. But yeah, if the solutions are down the tree, then you're not like winning anything by using DFS.
Like problems, do you think DFS with iterative deepening would be like useful?
In general, okay, so the question is, so in what problems do we think DFS iterative deepening is useful? In general, if like there are problems that I think BFS is going to be useful, usually DFS iterative deepening is useful. The reason I would think that is like there is some structure about the problem that I would think I would find my solution earlier. So if I have some reasons about the problem, about the structure of the problem that I think solutions are low depth, I should use some of these algorithms. And then DFS with iterative deepening, in terms of space, it helps too. So might as well use that. All right, so in terms of space, it's going to be order of small d now. So in terms of space, order of small d. And then in terms of time, it gets the same benefits of BFS. So that's nice. And then again, like because it has this BFS out of the loop, it has the same sort of constraint on the cost. It's got to be a constant constraint that's positive. Right? So that is our table. And again, in looking at this table in terms of time, we're just not doing well, right? Like we have this exponential time algorithms here, and we could avoid the exponential space with using something like DFS iterative deepening, but still this time thing is just not that great. And what we want to do now is we want to talk about search algorithms that bring down this exponential time to polynomial time somehow. And there is no magic. We'll talk about how. And dynamic programming is the first algorithm. Okay. Yes?
DFS ID is d to the d time and O of d space.
So the way iterative deepening works is it sets the level, let's say level is 1. So if level is 1, I'm going to do a full DFS. Okay? Because I'm doing a full DFS, in terms of space, it's the same as DFS. In terms of space, it's just the same as the length where we find the solution. Let's say the length where I find the solution is small d. So now I say level is 2. When the level is 2, I'm going to do a full DFS. Okay? So when I do a full DFS, then in terms of space, I need to just remember my parents. So that's why it's order of d in terms of space. And in terms of time, it's order of b to the d, because if I find my solution here, I'm done. I don't need to like explore anything else. And then that is exponential, but the exponential in this smaller depth as opposed to the longer depth, similar to BFS. All right.
I still don't understand why, let's say like the small d is the same as the big D, right? Then
Okay, so that's a very good question. So I think I know it is. So you're asking small d, if small d was the same as big D, if I had my solutions down here, well, why am I like differentiating here between small d and big D, right? Is that what you're asking, or am I?
ask if it's like if the depth is quite large, like small d is large, then why is the time also a function of d? As in, why wouldn't it be like d times b to the d?
Oh, I see what you're saying. So you're saying, okay, like when I'm performing DFS iterative deepening, then I'm doing DFSs. So sure, it's order of b to the d for each of them, but then I'm doing d of them. And if d is really large, I should put that here. Sure, I do agree that is the right time. But again, I'm like, in the case of this exponential, this is so bad that we are just dropping that. Like we don't even worry about that extra d that comes in. But it is true. You need to have that extra d, like in general, if you want to talk about it. Kind of want to move on to dynamic programming, but last question there.
Just to follow on to that, presumably though you're saving the work that you've done during the prior iterations, so you're not really computing anything larger than O to the B capital D, correct?
Yeah, that's right. The worst case scenario is O to the B capital B. All right. So let's move to dynamic programming. Okay, so what does dynamic programming do? So maybe I'll still use this because I might need to use this thing later. Okay, so I'm gonna erase my tram problem here. Okay, so the idea of dynamic programming, we have already seen this in the first lecture, is I have a state S, and I want to end up in some end state, but to do that, I can take an action that takes me to S prime, right? I can end up in S prime by cost of S and A. I can take an action that ends up in S prime. And then from there, I can do a bunch of things. I don't know what, but I'll end up in some end state. Okay? And what I'm interested in actually computing is for this state S is to find what is future cost of S. Okay? And this part of it is future cost of S prime. And I don't know what it is, but I can just leave it as future cost of S prime. So if I want to find what future cost of S is, maybe I should make this a little bit to the right. One second. I'm going to write cost of SA for this edge. I'm going to erase this. What I'm interested in finding is future cost of my state S. Well, what is that equal to? Well, that's going to be equal to this cost of SA, right? Like at state S, I'm going to take action A. So it's going to be cost of SA plus future cost of S prime. Again, I don't know what that is, but that's future Dorsa's problem. So this is future cost of S prime. And then you might ask, well, what is A? Where does A come from? How do I know what A is? I don't know. I'm going to pick an A that minimizes this sum. I'm going to put this around it. Okay? So future cost of S is just going to be equal to minimum of cost of SA plus future cost of S prime over all possible actions. And it's going to be 0 if we are in an end state. If is end of S is true. Okay? So if I already know I'm in an end state, then there is no future cost. That's going to be equal to 0. Otherwise, future cost is just going to be cost of going from S to the next state, and then future cost computed from there. Okay? So that is just how one would go about formalizing this problem as a dynamic problem, and dynamic programming problem. And how do I find what S prime is? Well, I wrote this successor and cost function in my code. Remember, like we know how to find the successor given that we are in state S and we are taking action A. So S prime is just calling that successor function over S and A. All right, so let's go back to some route finding example. So this is a slightly different route finding example. So let's say that we want to find the minimum cost path from going a city 1 to some city n in the future. Moving forward, we can always just move forward. And it costs Cij to go from city I to city j. Okay, so this is my new search problem. Okay, so this is kind of how the tree would look like. So if I want to draw the tree search for this, I can start from city 1, I can end up in city 2 or 3 or 4. Then if I'm in city 2, I can end up in 3 or 4. If I'm in 3, I can end up in 4, right? Like this is how it will look like. I can have a much larger version of it. If I'm talking about going to city 7, then I have this type of tree. And by just like looking at this tree, you see all these subtrees just being repeated like throughout, right? If you just look at 5, like future cost of 5, it's going to be the same thing, right? It's just going to be the same thing throughout. And if I use like something like tree search that we have talked about, then I have to like go and explore like this whole tree, and then it's going to be really time consuming. So the key insight here is future cost, this value of future cost only depends on state. Okay, so it only depends on where I am right now, and because of that, maybe I can just store that the first time that I compute future cost of 5, and then like in the future I just call that, and I don't like recompute future cost of 5. Okay, so the observation here is future cost only depends on current city. So my state in this case is current city, and that state is enough for me to compute future cost. All right, so if you think about what we have talked about so far, like we have thought about like these search problems where the state, we think of it as the past sequence of actions and the history of actions you have taken and all that. But right now for this problem, like state is just current city. That's enough. Okay. So and because of that, we are getting all these exponential savings in time and space because again, I can compute future cost of 5 there and collapse that whole tree into this graph, and just go about solving my search problem on this graph as opposed to that whole tree. Okay, so that's where you get the savings from dynamic programming. And I just want to emphasize that again. Let me actually do this. So the key idea here is, like I was saying, there's no magic happening here. The key idea here is how to figure out what your state is. Like it's actually important to think about what your state is. In this case, we're assuming the state is summary of all past actions that we have taken, sufficient for us to choose the optimal future. Okay, so that's like a mouthful, but basically what that means is the only reason dynamic programming works, and for this particular example we just saw, is the state, the way we defined it, is enough for us to plan for the future. Like I might have a different problem where the state, like I defined a state in a way that it's not enough for me to plan for future. But if I want to use dynamic programming, then I got to be smart about choosing my state because that is the thing that decides for the future. So for example, for this problem, like I might visit city 1, then 3, then 4, and then 6. And for solving this particular search problem, I just need to know that I'm in city 6. That is enough. Okay? But like maybe I have some other problem that requires knowing 1, 3, 4, and 6. And then because of that, maybe I need to know the full tree. Okay? So this is where the saving comes from, like figuring out what the state is and defining that right. All right, so we'll come back to this notion of state again and then think about the state a little bit more carefully. But maybe before that, maybe we can just implement dynamic programming real quick. All right, so let's go back to our tram problem. I'm back to the tram problem. And let's implement dynamic programming. Okay, so how do we do this? We're basically just writing that like math over there into code. That's all we're doing. So we're going to define this future cost. If you're in an end state, we're going to return 0. If you're not in an end state, we're just going to add up cost plus future cost of S prime. How do we get S prime? Well, we're going to call this success and cost function. So we can get action, new state, and cost. And then we're going to take the minimum of them over all possible actions. So minimum of cost plus future cost of new state. That is literally what we have on the board. Okay. All right. And we are returning the result. So that is future cost. What should dynamic programming do? It should return future cost over initial state, right? Start state. And you return the history if you want. In this case, I'm not returning the history. Okay, so how do I get savings? Well, I got to put a cache, right? That's the only way I'm going to get savings. So that is where I put the cache. And if the state is already in the cache, I'll just call my cache. Otherwise, I don't. There's a question there.
What's giving us future cost again?
What's that?
How are we getting future cost?
How are we getting? Say that again. Sorry, I didn't.
So future cost takes a state, but what actually is there like do we actually have like a function implemented to like calculate future cost, or is that like
So future cost is going to be, so we have this function, right, future cost over state, but you're going to call future cost, so future cost over state is going to be equal to cost of state and actions. In this function, I'm saying all possible actions, try that out, plus future cost of S prime, and S prime comes from the successor and cost function, successor and cost function. All right, so, and then, and so we do the caching, the proper caching type of way of doing this too. And now we have dynamic programming. So we can basically call this over our tram problem. So I'm gonna move forward. Okay. So let's do print solution, dynamic programming over our problem. You can again play around with this. The only way I'm checking this is if it gives me the same solution as backtracking search, because I knew how that works, right? So let's just call it on 10, and it gave me the same answer. So I can play around with this. Okay. All right. So let's go back. Okay. So one assumption that we have here to just point out is we're assuming that this graph is going to be acyclic. So that's an assumption that we need to make when we are solving this dynamic programming problem. And the reason is, well, we need to compute this future cost, right? For me to compute future cost of S, the S prime, I need to have thought about, for me to compute future cost of S, I need to have thought about future cost of S prime. So there is kind of this natural ordering that exists between my states. So if I think about an example where there are cycles, then I don't have that ordering, right? If I want to compute, let's say I want to go from A to D here, and I don't B, C. So if I want to compute future cost of B, I don't really know if I should have computed future cost of A before or C before, or what order should I have gone to compute future cost of B. So you actually need to have some way of ordering your states in order to compute these future costs and apply dynamic programming. So that's why we can't really have cycles when we think about this algorithm. But we are going to talk about uniform cost search, which actually allows us to have cycles in a few slides. Yes.
Runtime of the dynamic programming.
So the runtime of this is actually polynomial time in the order of states. So order of n. Yeah, O of n, where n is the number of states. Yeah. Okay. All right. So let's talk about the idea of states a little bit more, because I think this is actually interesting, right? So let's just reiterate. What is a state? State is a summary of all past actions sufficient to choose future actions optimally. Okay. So everyone happy with what state is? So now what we want to do is we want to figure out how we should define our state space. Because again, this is an important problem, right? How we are defining state space is the thing that gets the dynamic programming working. So we got to think about how to do that. So let's go back to this example and let's just change that a little bit. So this is the same example of I'm going from city 1 to city n. I can only move forward, and it costs Cij to go from any city I to city j. And I'm going to add a constraint. And the constraint is I can't visit 3 odd cities in a row. Okay? So what that means is maybe I'm in state 1, and then I went to state 3, or city 1, I went to city 3, and then after that, can I go to city 7? Well, no, based on this constraint that I've added, I can't do that. Right? So I want to define a state space that allows me to keep track of these things so I can solve this new search problem with this new constraint. So how should I do that? So in the previous problem, when we didn't have the constraint, our state was just the current city. Previously, we just cared about the current city. And the reason we cared about the current city is we are solving this search problem. We end up in a city, we need to know how I'm going, where I should go from 3. So I should have my current city in general, right? So for the previous problem, without the constraint, current city was enough. But now current city is not enough, right? I actually need to know something about my past. Okay? Yes.
have a count of how many test odd states?
Yeah, that's actually a very good point. Right. So one suggestion is have a count of how many odd states. Another maybe like, and maybe the first thing that would come to our mind is something simpler. So maybe we say, well, the state is, maybe I'll write previous city, just to be similar to this slide. The state, like one might say, well, the state is previous city and current city. Okay, so this is one possible option for my state, right? Because if I have this guy as my state, and then that is enough, right? Like if my current city is 3, I know my previous city was 1, I know I shouldn't go to 7. Like that's enough for me to make like future decisions, okay? But there is a problem with this. Well, what is the problem? So I have n cities, right? So current city can take n possible action and n possible states. Previous city can also take n possible options, has n possible options. So if I think about the size of my state space, it is n squared, if I decide to choose this state. Okay? If I decide to choose this state, I'm going to have n squared states. And remember, we are doing this dynamic programming thing, like we need to actually like write down like how to get from all those states. That's going to be big. But there is an improvement to this, and that's the improvement that you suggested, which is I don't actually need to have this whole giant previous city which has n options. I can just have a counter to just know whether the previous city was odd or not. Like that's enough, right? Like if I don't care if it was 1 or 3 or whatever, right? Like I just care to know if previous city was odd or not. So another option for, I'll write it here, another option for my state is to know if previous was odd or not. And then I need to know my current city again, right? Current city, we need that because like we need to know how to get from there. And then this brings down my state space. Like how does it bring down my state space? Because, well, what's the size of my state space? This guy can take n possible states. If my previous city was odd, that's 2, right? Like, so I just brought down my state space from something that was n squared to 2n. And that's a good improvement. So in general, when you're picking these state spaces, you should pick the minimal, like sufficient thing for you to make decisions. So it's got to be a summary of all the previous actions and previous things that you need to make future decisions, but pick the minimal one because you're storing these things and it actually matters to pick the smallest one. So here is an example of like exactly that. So my state is now this tuple of whether the previous city was odd or not and my current city. So if I start at city 1, well, like I don't have a previous city and I'm at city 1. I could go to city 3 and I end up in odd and 3. I could try to go to city 7. Well, that's not possible because now I have visited 3 states and I end up here and there are like the rest of the tree. You can have any other examples. So the way I'm counting this is how many, so my state is a tuple of 2 things, right? If the previous city is odd or even, I have 2 options here. It's either odd or even, that's 2. And then my current city, and I have n possible options for my current city. It could be city 1, city 2, city 3, so that's n. So I have n options here, I have 2 options here. That's why I'm saying my whole state space is 2 times n. Okay? All right. Okay, so let's try out this example. Let's not put it in. Just talk to your neighbors about this, and then maybe if you have ideas, just let me know in a minute. So, okay, so what is the difference here? So we're traveling from city 1 to city n, and then the constraint has changed. Now we want to visit at least 3 odd cities. So that's what we want to do. And then the question is, what is the minimal state? Talk to your neighbors. All right, any ideas? Any ideas? What is a possible state? Like, don't worry about the minimal even, like for now. Like, what do I need to keep track of? Number of odd cities? Yeah. Okay, so is that it? Do I need to just know number of odd cities?
Or number of odd is about your
So what I meant is I also need to have current city, right? So, okay, so one possible option for this new example, I'm gonna write that here, is I want to visit at least 3 odd cities. I also need to know my current city for any of these types of, like, not any of these types of problems, but for these particular problems that I've defined here, I need to know where I am. So I need to know what my current city is. So that is given, like I need to have that, okay? So I want to see at least 3 odd cities. So one possible option is to just have a counter and keep counting number of odd cities. Okay? So this could be one potential state. Okay? Yes.
Or could it be 1, 3, 1?
So okay, so the question is, do the cities need to be different? The way we are defining the problem is we're moving forward. If I'm in 1, like I can just move forward. I can't like stay at 1 or I can't like go back. So we're always moving forward. But when we talk about the state space, we're talking about the more general like setting. Like some of that 2n might not even be possible, but that's what you're counting. Okay? All right, so this is one option, but I can actually do better than this. Yes.
Off by saying you need at least 3 odd cities, and then you need at least 2 odd cities, then you need at least 1 odd city, and then you're done,
right? So a suggestion there is you can have like you can start by saying you need at least 3 odd cities, then you need at least 2 odd cities, then you need at least one odd city, and then you're done. And one way of formalizing that's exactly right. Right? I don't care if I have 4 odd cities now or 5 odd cities. Like as long as I have like above 3, that's good enough, right? 1 odd city, 2 odd city, 3 odd city. Above that is just 3 plus. Like that's enough for me. Okay? So if I have this, then the state space here is going to be n options here, and number of odd cities, it's around n over 2, so it's going to be n squared over 2. But if I use this new suggestion, where I don't keep track of 4, 5, 6, 7, I just keep track of 1, 2, and 3 plus, then my state space ends up becoming 3 times n, and I can formally write that as S is equal to minimum of number of odd cities and 3, and then current city, you need the current city. And with this state space, then the size is equal to 3n. Okay? So I just, again, brought down n squared to n, and that's a nice improvement. Yes?
Not also need an option for 0 odd cities visited so far?
0. We're starting from city 1, so we're already counting that in, but yeah, like if you have 0 odd cities, that's a good point too. All right, so I gotta move. Okay, so that was that. This is how it will look like. Like you can think of your state space like this again as a tuple of I visited 1, 2, 3, and then the cities. I have another example here. You can think about this later and yeah, like work it at home. But basically the question is, again, you're going from city 1 to n, and you want to visit more odd cities than even cities. What would be the minimal state space? But we can talk about it offline. So the summary so far is that state is going to be a summary of past actions, sufficient to choose future actions optimally. And then dynamic programming, it's not doing any magic, right? It's using this notion of state to bring down this exponential time algorithm to a polynomial time algorithm, and with the trick of using memoization and with the trick of choosing the right state. Okay? And we've talked about dynamic programming and how it doesn't work for cyclic graphs. And now we want to spend a little bit of time talking about uniform cost search and how that can help with the cycles. So if you guys have seen Dijkstra's algorithm, this is very similar to Dijkstra's. Like, yeah, so it's basically Dijkstra's. But all right, so let's actually talk about this. So the observation here is that when we think about the cost of getting from start state to some S prime, well, that is going to be equal to cost of going from S to S prime and then some past cost of S. And then in dynamic programming, like we make sure that we have this ordering and these things are computed in an order, so we're not worried about like visiting the state like multiple times. But in uniform cost search, we might visit a state multiple times, and if we have cycles, we don't know what order to go. But the order we can go is we can actually compute a past cost, a suggested past cost, and basically go over the states based on increasing past costs. Okay? So let me actually, yeah, so uniform cost search, what it does is it enumerates states in an order of increasing past costs. So, and in this case, we need to actually make an assumption here. We need to assume that the cost is going to be non-negative. So I'm making this assumption for uniform cost search. So here is an example of uniform cost search running. Oh, we don't have internet. Yeah, there is a video of uniform cost search running in action. If I have time, I'll connect to internet and get it working. But so let's talk about the high-level idea of uniform cost search. So in uniform cost search, we have 3 sets that we need to keep track of. One is explored set, which is the states that we have found the optimal path to. These are the states that we are sure like how to get to. We have computed the best path possible to get there. We are like done with them. Okay? Then we have another set called a frontier, where this frontier are the states that we have seen, we have computed like a cost of getting there, like we know somehow how to get there and what would be the cost, but we're just not sure about it. Like we're not sure if that was the best way of getting there. Okay, so the frontier, you can think of it as a known unknown. I know they exist, but like I'm not sure what's the optimal way of getting there. And then finally, we have this unexplored part of states, and these unexplored part of states, I haven't even seen them yet. I don't even know how to get there, and you can think of it as more of an unknown unknown. So that's like how you would think about these 3. So let's actually work out an example for uniform cost search. I'm actually going to do this one. So I'm just going to show how uniform cost search runs on this example. So I said we are going to keep track of 3 sets: unexplored, frontier, and then explored. Okay? All right, so everything ends up in unexplored at the beginning, A, B, C, and D. And what I want to do is I want to go from A to D. That's what I want to do. Okay, so I want to find the minimum minimum cost path to get from A to D, given that I have this graph. Okay, so what I'm going to do is I'm going to take my initial state, that's A. I am going to put A on my frontier, and it costs 0 to get to A because I'm just starting at A. Okay, so that's on my frontier. Then the next step, what I'm going to do is I'm going to pop off the thing with the lowest cost from my frontier. There's one thing on my frontier. I'm just going to pop off that one thing off my frontier. I'm going to put that to explored. The cost of getting to A is 0. And then what I'm going to do is, after popping it off from my frontier, is I'm going to see how I can get from A to any other state. So from A, I can get to B. That's one option. And with the cost of 1. So from A, I can go to B with the cost of 1. Where else can I go? I can go to C with a cost of 100. Okay, so what I just did is I moved B from unexplored to frontier, and then I know how to get there from A, and I moved C to frontier, and I know how to get from there. Okay? So now it's the next round. I'm looking at my frontier. A is not on my frontier anymore, it's in explored. And I'm going to pop off the thing with the best cost of my frontier. Well, what is that? That's B. So I'm going to move B to my explored. The best way to get to B, I already know that, right? That's from A to B. Everything is good. Okay? So now that I've popped off B from my frontier, I'm going to look at B and see what states I can get to from B. From B, I can go to A, but A is already in explored. Like, I already know the best way to get to A, so there's no reason to do that. From B, I can get to C. And if I want to get to C, then I can actually get to C with the cost of 1 plus whatever cost of B is already, 1. So what I'm going to do is I'm going to erase this because there's a better way of getting there. And that's from B. Okay? And then from B, I can get to D. So I'm going to move D from unexplored to frontier. I can get to it from B. And then how do I get to it from B? There's a cost of 101, right? Because 100 plus cost of getting to that. Okay? All right, so I'm done exploring everything I can do from B. Going back to my frontier again. So these two are not on my frontier. I just have C and D on my frontier. I'm going to pop off the thing with the best cost. That is C. I'm going to move that to explored with the cost of 2. And the best way to get that is from B. Okay, so we're done with C. And then we're going to see where we can go from C. From C, I can go to A. Well, that's done. That's already on export. In the export set, I'm not going to touch that. Similar thing with B, already in export. Don't need to worry about that. From C, I can get to D, right? And if I want to get to D from C, well, what would be the cost of that? It would be 2 plus 1. So I can update this and have 3. And I can update the way to get to D from here. And then we're done. We go to frontier. The only thing that's left on the frontier is D. I'm going to just pop that off, and then I'm going to add that to export, and that is 3. And that's what I have in my export. So the way to get from A to D is by taking this route, and it costs 1. So A, B, C, and D. Okay? Is that clear? All right. Okay, so there are 2 slides left, and they're probably going to kick us out soon. So I'll do this next time. So yeah, the two slides left is one is going to just go over the pseudocode. So take a look at that. The code is online. And there's a small theorem that says this is actually doing the right thing. I'll talk about that next time.